Okay, I make it 20 past, so let's get started again. Next, we have Karim Thebault. Karim is a senior lecturer at the University of Bristol and is an active member, contributor, and organizer within the Bristol Centre for Science and Philosophy. Karim mainly works within philosophy of physics, focusing on time and symmetries in classical and quantum theories of gravity. Karim is also really at the forefront of the recent focus in philosophy of science on analog experiments, and is going to be drawing on some of that work today in his talk titled Universal Reasoning. Karim's posted 2 papers in the chat, which he's going to be drawing on heavily from this. One's on the limits of experimental knowledge, and the other is on the universality of Hawking radiation. So I'll hand the virtual floor over to Karim.
Thanks a lot, David. Can everyone hear me okay? So I just want to say, like, this, I've really enjoyed the conference so far, and I think that the lineup's been fantastic. And I particularly enjoyed the talk so far today as well. And so in that vein, I really do want to emphasize a kind of coherence with some things that Hans was saying in the morning that I think is absolutely essential for us to focus on real experimental practice and real knowledge claims made by scientists to try and understand better how we should understand empirical knowledge or empirical claims within science. And the messiness of actual scientific experiments ultimately is quite important for that process. And so what I'm going to talk about, it mainly relates to 2 kind of areas of science which I think we need to focus more on, in particular astronomy and cosmology, and analog experiments, which will be the main focus. And this, I think, connects broadly with the theme of empiricism, and I'll talk about a view I'll call liberal empiricism. I'm not taking this to be a fully fleshed out empiricist stance or empiricist view. I'd be very interested if the extent to which members of the audience think that the things I'm saying compatible or incompatible with various of the more well-developed empiricist views. What I'd like to do is really offer both a descriptive account focusing on contemporary practice in astrophysics and analog experiments, particularly quantum simulations, but also have some kind of normative force to it. How scientists can justify their knowledge claims more clearly, but also extend those claims as well. The main kind of focus is you'll see pictured in the slides here is these platforms called cold atom simulators, which can be used to simulate vast range of quantum phenomena. And yeah, this builds on quite a lot of different collaborations of the long list of people listed there. I take full credit for any errors or confusions in the talk, however. So let's start where I said we'd start. Let's start with scientific practice. And so some years ago now, the first in a series of experiments by Jeff Steinhauer and his group in Tel Aviv, and that they claim the observation of quantum Hawking radiation and its entanglement in an analog black hole. More recently, and with less fanfare, a whole variety of other analog experiments have been conducted, almost always published in Nature. This one from, I think it's 2018. In this, what's quite interesting is that the kind of conclusion to the start of the introduction runs as follows. The details of the actual paper we're not going to focus on too much. One may yet learn using this universality, the universality which I'll talk about quite a lot in the talk, from experiments with ultra-cold gases about the fundamental aspects of dynamics studied in cosmology and quantum chromodynamics. So the idea is by using these cold atom simulators plus this thing called universality, which I'll talk about shortly, you can learn from experiments on cold atom gases about things like cosmology and quantum chromodynamics that happen in a completely different energy regime or completely different in the early universe, for instance. Another paper from the same edition of Nature, the end of the conclusion runs as follows. Universality would open up the possibility of using, for example, cold atom setups at the lowest energies to simulate important aspects of the dynamics of currently inaccessible systems at the highest energies, such as those encountered in the inflationary early universe. note that the word inaccessible explicitly appears here. So you can, and I could find many, many more examples of this kind of reasoning in contemporary experimental science. Scientists are already making use of some form of inductive inference towards universal behaviors that exist in distinct types of systems. So this is generic and it's been done in many contexts for a long time. How do we justify this type of reasoning in general? Can we do it via triangulating with different modes of inductive reasoning? And in particular, and most controversially, and I think most fascinatingly, can we apply this form of universal reasoning to inaccessible types of system, as seems to be indicated by the final quote I gave? So what I'm going to argue is that the limits of what we can know about from experiment are set by the mitigation of what I would call reasonable doubt via the triangulation of different forms of inductive inference. And we can and do in practice learn about inaccessible systems through experiment uncontroversially all the time. Furthermore, we can construct dialectically convincing forms of inductive inference towards the existence of phenomena of inaccessible types based upon the combination of universality arguments and enumerative induction over distinct tokens of accessible types. The strength of such universal reasoning, and I'm not saying just because it can be dialectically convincing, it doesn't have to be particularly persuasive. The strength of such reasoning, I'll argue, crucially depends upon whether the universality arguments have a property which I would like to call integration. And this is where the theoretical basis behind the invariance at type level and the token level are mutually consistent. So I'll hope to convince you of at least some of these conclusions by the end of the talk. So we'll talk in the first part. I won't talk about universality, and I'll focus more on examples from astrophysics, in particular stellar nuclear synthesis. And then in the second part, I'll move on to the context of universality arguments and these kind of interesting intertype modes of reasoning that seem to be extremely relevant for what scientists are doing with analog simulations. And I think I would hope that a lot of the things I'll say, certainly at the beginning of the talk, will verge on platitudes, but it's useful to get a terminology to discuss them for the second part of the talk. So the first thing I would like to talk about is this notion of phenomena and observable and unobservable distinction. And I'm not really going to argue for this in detail. What I would say is, I'd say self-evident, in fact, is that unobservable phenomena are important to science. Before we argue that, we really need to, or before we state that, we need to know what we're talking about. So I think it's useful to talk about phenomena in terms of quantitative or qualitative empirical properties of a system which correspond to a numerical value of a parameter or characteristic behavior of a parameter. We can then distinguish between data gleaned from a particular experiment or observation and the general class of observable phenomena about which scientists may reasonably draw conclusions, given the data and given an appropriately validated experimental procedure, of course. And in a really wonderful article from 2007, which I strongly recommend, Michele Massimi argues, building on earlier work due to Bogan and Woodward, that in scientific practice, we find unobservable phenomena, particularly in the context of experimental particle physics. And what I think is useful then is to be able to distinguish, and so I'm mainly going to be focusing on just different types of unobservable phenomena and the way that we can justify knowledge claims with regard to them based upon experiment, not the distinction between observable and unobservable. So what I think is useful is to distinguish between unobservable phenomena that correspond, that are manipulable, and unobservable phenomena that are unmanipulable. And a simple example of this would be something like the spin on an electron, which we can manipulate, but is unobservable. And it's a phenomena, it corresponds to a parameter. We can then think by contrast, and this is the broad and very familiar category of phenomena discussed in astrophysics. We can think about unmanipulable phenomena that is what I'll call accessible. So the classic example, which I think has now become the standard example, which is great in philosophy of science talks, is the black hole mergers and gravitational waves. These are accessible. These are clearly not manipulable, because not only did they happen a very long time ago, but we wouldn't have the energy to manipulate them even if we were near them, anything like it. But they're accessible in that we can receive causal signals from them. So in general, I'll think about accessibility as meaning that we can at least get one-way causal access to the system. We might not be able to causally influence it, but we can receive causal signals from it. And we could then think about manipulability as having some form of two-way causal access that's mediated through some observational system or apparatus. And so far so good. And I think so far so fairly uncontroversial that scientists make claims about unmanipulable, accessible phenomena, and we have good reasons to justify those claims in some instances. What's more controversial, and perhaps shouldn't be more controversial, is the context of unmanipulable, inaccessible phenomena. That is, phenomena that we can neither manipulate nor even get causal signals from. We can't access it. And a kind of quite simple example, which is interesting in the sense because it's time indexed, would be the physics of the interior of the sun or of any star. And certainly until the early 2000s, there was no way at all known to get causal access to information about what went on in the center of the sun, for the simple reason that photons or other form of electromagnetically strongly coupled kind of particles or media are going to take billions of years to get through the dense plasma of the sun. So we'll never get any signal from inside them. Subsequently, it was found that we could actually access the interior of physics of the sun via neutrino evidence. That notwithstanding, the interior of the sun is inaccessible photonically, and for a long period until this neutrino evidence was found, was inaccessible simpliciter in practice. So we have this kind of framework for differentiating between these different types of unobservable phenomena. The question then comes, how can we understand, or how should we analyze the forms of inductive reasoning we use to justify scientific beliefs about these phenomena? So what kind of phenomena can we gain knowledge about? What factors place limits on the strength of this knowledge? In particular, you might think perhaps that phenomena have to be manipulable for us to have knowledge about them, or that phenomena that we can manipulate have a special category. Perhaps we should only be realists about them. People have claimed that in the literature. Weaker and more, I think, much more plausibly, you might say that accessibility is the we have to at least be able to access the phenomena to be able to make knowledge claims about them. Let's see where we go. In particular, like in the one of the papers that I provided the link for with Peter Evans, we argued that the limits of experimental knowledge shouldn't be taken to be circumscribed by manipulability or accessibility. And we talked about the example of stellar nucleosynthesis and gave quite detailed kind of breakdown of the way that scientists reason about stellar nucleosynthesis to try and justify this claim. And I'll review some of the kind of brief details about that shortly. But before that, I think it's very useful to just give a framework for the argument, for the analysis, just to talk about this kind of quite old idea of uniformity principles, and that seems to be kind of most interestingly relevant from the kind of very nice discussions of the problem of induction. So let's just talk quickly about that. So there's a huge literature on the problem of induction, and I'm not in any way going to be kind of analyzing it here. But one of the things, the kind of threads which I think is quite useful, is the following. So there's this argument that Hume's argument itself operates under something like a quantifier shift fallacy. And that's because ultimately he fails to recognize the diversity of uniformity principles. He assumes that there's a single uniformity principle, but in fact that there are multiple. And once we recognize this, the argument seems to not carry any water. Now, I think plausibly you might say that this response doesn't really solve the problem. It converts it into a justificatory regress, which might perhaps be better than the kind of quantifier fallacy, but still leads to some kind of case needs to be answered. And I'm not going to comment on this. And I think for my purposes, I'd like to bracket the kind of problem of responding to radical inductive skepticism. But what I do think we should really have to be careful to recognize is that people like Sober, Akasha, and Norton are totally right that there clearly are multiple and diverse uniformity principles operating in science. Let me just name a few. Temporal uniformity, past phenomena resemble future phenomena. Spatial uniformity, local phenomena resemble distant phenomena. Intra-type uniformity, which is incredibly important. Between different tokens of the same type, we reason that they must behave the same. These electrons resemble those electrons. We don't need to do experiments on every single token of the type electron to be able to make very, very robust inferences about electrons. Another notion of uniformity, which I think is underappreciated, and certainly discussions with James Ladyman, Anna Maria Kretsu, and Karen Wiesner have made it really clear to me is scale uniformity, or the importance of scale in physical reasoning. We have phenomena at different spatiotemporal or numerical scale, and in some cases, not always, in some cases we reason about uniformity between them. And this is actually quite relevant for the kind of general class of kind of analog experiments, where we might think something like, when we're doing aerodynamics based upon a model plane, we're using something like a kind of scale uniformity between the relevant aerodynamics between the toy model's plane wing and the real plane wing. And we have good reason to believe that the relevant scale won't make a difference, and that justifies our inductive reasoning from toy planes to real planes. And this isn't supposed to be an exclusive or exhaustive list. Of course, in practice, real scientific inferences are phenomenally complex and mix together all these different forms of uniformity in a way that scientists are not going to be able to pull apart and say, this is that uniformity, this is that uniformity. But in practice, in principle, it's useful to make these kind of distinctions, in particular when we're thinking about a form of selective skepticism, which would be regard to one of these but not to the others. And that's what I'm going to focus on for majority of the talk. In particular, if we thought about a further notion of uniformity, which is kind of like the third one, but pushed up a level. So this would be intertype uniformity between different types of systems. So this magnet's critical behavior, this magnet's phase transition resembles this fluid's phase transition in some relevant respect. So this is what I'll call intertype uniformity. We can, I don't think this is a particularly novel idea, and it's got lots of historical precedents. We might think that the mode of inference where we justify one form of uniformity principle based upon one of the others, we might call it inductive triangulation. So let's say inductive triangulation is the use of one or more forms of inductive inference to justify a further non-identical form of inductive inference in a dialectical context where one's interlocutor is not skeptical of inductive reasoning per se. So the case in which someone across the board, like Hume, doubts the viability of uniformity principles, saying, well, look, I can justify one based upon another doesn't seem a particularly good response. The idea is in a context where you're arguing with someone who's skeptical about some but not all inductive principles or uniformity principles, there's a straightforward way of you giving them convincing reasons to warrant a further uniformity principle based upon operation of the uniformity principles that they do accept. And so simple example to try and give you an intuition why it is plausible in some cases to think that there are inaccessible phenomena or inaccessible systems in which we should reason about, we should accept reasoning about, would be electrons outside our past light cone, or probably more correctly outside our past particle horizon. So these are things that we don't have causal access to, but we have a whole range of ways of reasoning or justifying reasoning between a source system that we have access to, an electron in our lab, and a target system, target phenomena that we don't have access to, the electron that's on the other side of the universe that we don't have any causal contact with. Because we can think about how the uniformity of electrons on the surface of the sun, electrons in our accessible paths, electrons on the Earth, these all point to a consistency in our reasoning regarding inferences between the electrons in one class and the electrons in another class. And the kind of collective triangulation of this reasoning gives us very strong reasons to believe that there's nothing special about the electrons outside our path-like code. This is essentially the cosmological principle, which is really needed to do most cosmological reasoning and astrophysical reasoning in any case. Just to give us a short way of referring to the type of skeptical argument that I'm taking myself to be responding to, we might just define reasonable doubt as doubt that's amenable to mitigation based upon inductive reasoning. So in this sense, the kind of argument that we're in, the dialectic, excludes from the get-go things like inductive skepticism, Cartesian skepticism, radical social constructivism. I take us to be in a context in which we at least accept some forms of inductive reasoning. And in that context, I don't think there's any reasonable, in principle, that we can't give dialectically convincing arguments to mitigate reasonable doubt regarding any form of inductive reasoning via this inductive triangulation, whether it be between types or between accessible and inaccessible systems. This is an in-principle claim rather than a claim that we will always or we should always accept these types of claim. The idea is just that there is, provided one is arguing with someone who isn't an inductive skeptic, potential inductive means to justify inferences about phenomena that are inaccessible or that relate to types that we haven't got, in particular, types that we haven't got access to. And so I'm kind of running out of time, so I probably won't go into this in detail. You can look at the actual kind of style of reasoning that scientists, particularly before the neutrino experiments, used to get very, very high degree of belief and very high confidence in the theory of the interior of the sun, and see that they're patching together things like observations on terrestrial nuclear accelerators, the laws regarding how long stars could live, depending upon which types of nuclear process went on within them, the atomic spectra, all together of exploded stars to see what their constitution is. All this together allowed them to have extremely well-justified claims about the physics of the interior of the sun without having access to the physics of the interior of the sun. And so I think what this justifies is some form of liberal empiricism, where we don't restrict the scope of phenomena about which we can gain knowledge about based upon experiment. And interestingly, this is not only more liberal than one would be unsurprised if it wasn't more liberal than Van Fraasen's form of empiricism, but it's in fact more liberal than certain forms of scientific realism that have been defended on this kind of detectorist account. There's some irony as a card-carrying anti-realist that I end up endorsing claims which some scientific realists would deny. In any case, the idea is that experimental knowledge is limited not by the accessibility of the target system, but by the available means for inductive triangulation. That is, the validation of the mode of inductive reasoning involved in the source-target inference via appeal to one or more distinct independent modes of inductive reasoning. So this leads to the more radical idea, which I'm going to have to speak about fairly quickly since I'm running out of time. Then in some circumstances, we can apply this to systems of different type, even when that type is inaccessible. Since we're virtually in Bristol, I couldn't resist giving a quote from our local hero, Michael Berry. He says as follows: saying that a property is a universal feature of a system is a slightly pretentious way in which physicists denote identical behavior in different systems. The most familiar example of universality from physics involves the thermodynamics near critical points. So the idea is essentially that you can start understanding certain parts of physical behavior, in particular related to phase transitions, in a way that's universal, it's independent upon the particular type of system that you're manipulating. Following Batterman, I think it's quite useful to differentiate between two features of a universality argument. That is the invariance of the property at token level, the particular details of the token system don't matter, and at a type level, the particular type of system doesn't matter. So the first is where the systems are largely, the details of the particular system are largely irrelevant for describing the behavior of interest. The particular way this fluid is arranged doesn't matter, or the particular way this magnet is arranged doesn't matter. And the second is where the system with completely different micro details will exhibit the same behavior, whether it's a fluid or a magnet doesn't matter. In our paper from 2019, Sean Greer, Patricia Palacios, and myself argue that when we're assessing universality arguments, what's absolutely crucial is a property we call integration. And that's where the theoretical basis behind the invariance found in the universality arguments at the token level and the type level are consistent, i.e. the universality and the robustness, the token level insensitivity details and the type level insensitivity details can be made consistent with each other. And so the actual universality arguments that are used in condensed matter physics that Berry and Batterman are focusing on really come from work in the 1970s. And this is, I think, along with the Standard Model, one of the greatest achievements of modern physics, without doubt. And so in this context, people like Wilson and Kadanoff use something broadly called the renormalization group framework, or the details of their application of it differ, based upon something called called fixed points or critical points in thermal contexts, which is a formal machinery to be allow you to argue that the particular features of the system don't matter, based upon very general kind of symmetry arguments. The idea that is crucial for our purposes is that when you use this fixed point structure to argue for universality, you get integration by construct. The way that you argue for type level insensitivity and token level insensitivity are engineered to be consistent. And this is what we pointed out in our paper was the crucial problem for the arguments for the universality of Hawking radiation. They're unintegrated. They aren't structured based upon fixed points, and in fact, you can show that the type level and token level invariance are to some degree in tension. So the arguments which are extremely token level robust, they don't depend upon the details, are very specific to largely fairly unrealistic idealizations about the nature of black holes, in particular, assuming that they're stationary and eternal. And so this means that trying to use this style of universality arguments is always going to be a little bit epistemically shaky. And I think that's a reasonable conclusion. Okay, so this is just the final bit. I might run over a little bit if that's okay, David.
Yeah, of course.
Okay, so university arguments, they're theoretical arguments. So in and of themselves, we should not believe them just because someone writes down some clever maths, of course. But we can support them by inductive means. In particular, we can support them by straightforward enumerative induction, in essence, on the types. So we support the inference for universality of some behavior across types by experimentally demonstrating the behavior in multiple exemplars of each type. And that's why we believe the universality arguments in condensed matter physics. In fact, the experimental demonstration of universality, in my knowledge, came first, but that's not really that's the context of discovery rather than the context of justification. So we actually find we experiment on fluids and magnets and show they display the same behavior predicted by Wilson and Kadanoff. It would, of course, not be reasonable for us to only do this based upon one experiment on one type. It's because we can investigate diverse types and show this that we believe these are the kind of inferences that these arguments justify. And I don't think it would be reasonable to say that if we have, let's say, some weird type of matter that we haven't ever experimentally constructed, and we have good theoretical reasons to put it inside one of the universality classes that the Wilson-Kadanoff framework predicts, it seems unreasonable to me to simply refuse to say that we can justifiably make inferences about this weird matter we haven't experimented. Because we've used these arguments in so many different contexts, we should trust them, at least to some degree. Where things get controversial and for me exciting is when we start pushing this a bit further. In particular, the original arguments that were given in a pair of papers with Radim Dardashti, Eric Winsberg, and the second one with Stefan Hartmann, we tried to push this to the context of black holes. And we tried to say we can, in fact, confirm informally in the first paper and in a Bayesian sense in the second paper, inaccessible phenomena in a type of system, black hole, which at least within the regime where we're talking about Hawking radiation is not accessible. And there's a response to this paper by Crowther et al. And a response to the response in the Evans paper, the paper with Evans I discussed earlier. And I won't go into the details of those arguments there. I just wanted to point out that ultimately the point that I'm perfectly happy to concede is that the lack of integration is a weakness. In order to make these kind of inferences, we can, I think, plausibly say if we construct multiple types of analog realization of black holes, and we have this universality argument, reasonably make an inference about Hawking radiation in real black holes. So if we can build a black hole, analog black hole out of Bose-Einstein condensates, out of optical media, out of 3 or 4, there's probably about 20 different proposals that have been made. And in every case, we find that Hawking radiation obtains. I think it's plausible to think that we have inductive evidence in favor of Hawking radiation in black holes. I don't probably think it's very plausible to say it's strong inductive evidence, precisely because not because black holes are inaccessible, but because the universality arguments are unintegrated. There is this tension between the token level robustness and the type level robustness. And so that just brings me to where I started. That I think these new kind of case of universality arguments combined with analog experiments that are focused on, in fact, non-thermal fixed points are particularly exciting for this reason, because the arguments in question are integrated. We have this kind of coherence between the total level and the type level robustness. It means the inferential power is potentially much increased. If we can build very diverse and different experimental systems which show the phenomena, and we have these very powerful integrated universality arguments, I think we can give convincing reasons to believe in phenomena in the early universe that we don't have access to. And this is just the conclusion recapped, but I'm at over time, so I won't read it again. And here's some references. Thank you very much.
Thanks so much, Karim. That was really, really fascinating. So yeah, we'll do the standard Q for question, F for follow-up, and please, as per usual, you can bracket whether or not you're a student. Yeah. Oh, I see Eric has a hand up. So yeah, Eric, do you want to go ahead?
Yeah, thank you. So Karim, you probably know this is not going to be very sympathetic. So just prepare yourself.